Good morning, everyone. Today's topic is raw materials, virgin, modified, and filled PTFE. So let's talk shortly about PTFE. PTFE, it's a fluoropolymer. As you all know, it can be virgin, modified, and we will see what does it mean, but it can be mixed also with several ingredients, and that's what we call PTFE compounds. But let's start from PTFE, virgin PTFE raw material. So basically, why we do like PTFE, why the industry like PTFE? Basically because it has outstanding properties, outstanding performances, but why? The main reason is the presence of the fluorine atom. Fluorine atoms it's the most electronegative atoms of the elemental table. Here we have two pictures. One is PTFE, the other one is polyethylene. As you can see, they are quite similar. We can see dark spheres, that's carbon, what we call carbon backbone. It's the core of the molecule. And outside we have two different spheres, dots. One is green, the other one is white. Green dots are fluorine atoms, bigger atoms, as you can see from the drawing. Hydrogen atom, they are smaller. As you can see on polyethylene, we still see the carbon. So carbon is, it likes to do some bonding. And what does it mean? It means that polyethylene has a lower chemical resistance, for example, because if something is going to attack these two chains, on the polyethylene, carbon has a weak bond, quite weak bond with hydrogen, and they want to do bonding with other stuff. On the polyethylene, polytetrafluoroethylene, PTFE, as you can see, we have fluorine atoms that are protecting the carbon backbone, and then the strong bond between carbon and fluorine. This is everything related to the properties of the PTFE. We will see more in detail about this, but remember, this strong bond between fluorine and carbon and the big atoms of fluorine that protects the carbon, this is what lead to the performance of PTFE. Basically, you can think PTFE can withstand to 300 degrees, 280 degrees. Polyethylene will melt, will degrade earlier. Why? Because the temperature is energy. We have a strong bond and the protecting layer of fluorine. You give high energy. For example, we have two parts, one of PTFE, one of polyethylene. We put in the oven at 200, 250 degrees. PTFE, nothing happens. Polyethylene will start to degrade. Why? Because the energy, thermal energy in this case, will be transmitted to the polymer. Polyethylene has a weaker energy bonding, and they will start to melt and then degrade. PTFE is very strong, and temperature up to 280 and 300 degrees, nothing happens to PTFE. So fluoride atoms is the key of PTFE. Basically, we are talking about polymers. So just a quick overview, what is a polymer? Polymer is a repetition of a molecule, in this case C2F4, that undergoes, so this molecule is called a monomer in polymer science. The monomer undergoes to a polymerization. The polymerization will lead to these very long macromoleculars that is a repetition of the same structure. So we have the monomer. After the polymerization, we will have a very long repetition of the same entity, the monomer. So we have talked, fluorine is the key of the properties of PTFE, but which are the properties of PTFE and PTFE compounds? Basically, PTFE is the polymer with the widest service temperature range. It can be used from cryogenic application minus 200 degrees up to 280 degrees, sometimes also higher temperature. But again, we already did the example, why can we stand to such a high temperature? Basically because the strong bond from fluorine, that fluorine wants to do, and it does with carbon, and also the chain that is a linear chain, very long, we will see shortly. The low coefficient of friction, everyone knows that PTFE is the best material for friction, I always like to do an example. If you take two ice cubes and you want to slide one on the other, you can imagine they will be pretty slippery. But if you take two parts of PTFE and you try to slide those PTFE parts one on the other, the coefficient of friction will be lower than ice to ice. So this it's incredible, and it leads to many possible applications of PTFE on friction application. The chemical resistance, again, like the surface temperature, there are no other polymer on the market that have the same chemical resistance of PTFE. Basically, PTFE is resistant to everything. There are no known solvents that can attack PTFE. Also, another important properties is the UV stability, the weathering. It has been done some tests on the field. Basically, some PTFE parts, they were placed in a desert for 25 years. And every year they were going and taking a part of this PTFE and they were doing mechanical tests. After 25 years in a desert, nothing changed. So the product after 25 years on the desert under high temperature, low temperature, rains, super high heat because of the sun, the polymer itself kept its properties as after the production. That's incredible. Low surface energy, this means that it is not wettable. If you try to place some water on PTFE, the water will try to make itself as spheres because it's hydrophobic. This is basically, everyone knows PTFE on coatings for bright pens. This is the reason, because of its surface energy. Also, another key feature of PTFE is the dielectric resistance. It's widely used as an electrical insulator, but why? Mainly because it keeps the dielectric constant, the same value of the dielectric constant in very wide frequency range. So you can use the PTFE at different range and you will have always the same output. This is really important in PCBs and application where you have to set your own parameters for electrical equipment. Also, another key feature of the PTFE is that it's non-flammable, so it's limiting the oxygen. This is widely used, for example, on wires. Every airplane out there, they have all the wires are covered of PTFE tape, because if something will happen, they don't have to let the flame to go on, so it will PTFE will try to slow down the fire, and that will be really helpful, for example, in a plane, because you don't want some fire in the plane, but also in houses and in many applications. Okay, let's go in deep on PTFE materials itself, powders and grades. We do have, as we mentioned by the title of this webinar, we have virgin PTFE, modified PTFE, and PTFE compounds, filled PTFE. All these three families of material, we have a powder that we've seen in the last webinar, the production process of PTFE. So we have a powder, we take the powder and we do semi-finish and then finish parts. But also in last webinar, I told you that I would explain you better different PTFE grades, powder grades. So any of these three families, virgin, modified, and filled PTFE, can be found in three different forms: non-free flow material, free flow material, and pre-sintered. Basically, what they are. Non-free flow material is a flaky material that doesn't move really well. It tends to compact, but is the best product to do the production. If you can process the non-free flow material, you will have the best performance out of the PTFE. Free flow material is a granulated grade, so we take the non-free flow material, we do some granulation, and then we will have these small spheres that wants to flow, free flow, that's the name. This is really helpful for thin wall production tubes or thin wall anyway, and automatic molding. Then for who have a attended the last webinar, we have talked about extrusion, and in extrusion we need a special grade of powder that is called presinter, so it's kind of a free flow that is pre-cooked. I have just here a couple of bags to show you the differences. This is basically a non-free flow virgin PTFE. As you can see, it doesn't flow. It's flaky and it tends to compact. So if we do like this, we will have some compaction inside here. Then we have a free flow material. Again, it's a virgin material, but look, when I try to flow, it tends to flow. I can't show it by this camera, but they are very small balls, spheres, so granulated. Then we do have a non-free flow of compounds. This is a bronze compound, and this is this is carbon, and this is bronze. But as you can see, they are almost, these are non-free flow materials, so they doesn't flow really well. Going back to our topic, virgin PTFE, we can have non-free flow, free flow, precinters, material. What is modified? Modified PTFE is a modification of virgin PTFE, and the modification of the chain. So we have seen the chain, the picture with green dots. If the raw material producer adds something to the recipe of the polymerization, they will have a ramification on that two linear chain, and that will be called modified PTFE. Modified PTFE has some feature that we will shortly see. Filled PTFE, it's basically a virgin PTFE. We add some filler inside, and we get a product that is PTFE plus the filler that was chosen. And we will see which are the most common filler and why we do always choose those. Also important to mention is the reprocessed PTFE, because as you know, we have to reprocess powder, but mainly for environmental situation, because we don't want to load the world full of scrap and things that that will have a very long life inside our earth. So we do always study ways to reprocess and use PTFE scrap. Mainly, the product that we can get from reprocessed powder is the second grade PTFE, but still with quite good performances. So this is, I guess, it can be important to things when we don't have an extreme application of PTFE, also about reprocessed PTFE, because this will help the world to have less scrap and landfills. Okay, fluorseals trades virgin PTFE under the PTFEs under the trade name of Flutec P. So Flutec P means PTFE families. We can have P virgin, we can have P modified, and PTFEs compounds. But we do also have, like we will see in the next webinar, thermoplastic material, for example, P. We pick under the Flutec K name. On virgin PTFE, we do have three main grades. The standard grade is called Flutec P1000. Premium grade means higher quality, better production process, better control, more consistent material, higher raw material grade. It's called Flutec P1500. That's our premium grade. And also the P2000, that is the medical grade application, USP Class 6 approved. I promise you that we would have seen the modified PTFE performance. So we already mentioned that modified PTFE is a change of the macromolecular of PTFE with this ramification. But why do we have to use modified PTFE? Basically because this ramification will lead to some better performance comparing to virgin PTFE. We will have a better deformation under load. PTFE is one of the problem of PTFE probably is the deformation under load. That means it doesn't resist to very high loads because the liner chain wants to slip one to the other. So this ramification of modified PTFE will help the PTFE to have a better deformation under load. And this is really helpful when we raise the pressure in our application, because we don't want the pressure to modify the shape of our seals or any kind of application. Modified PTFE is also more transparent. It is heat bondable and weldable, and that's quite useful in certain applications where we do have to weld different parts made of PTFE. PTFE doesn't like to be welded. Modified PTFE, it's quite easily weldable. Also, the flex life, the flexibility is improved compared to PTFE. So in certain applications where we do need the flexibility of the PTFE in a very long life cycle, for example, for diaphragm in diaphragm pumps, where we do have a diaphragm that have to keep doing a flex life, modified PTFE will have a better performance compared to virgin one. Also, it's not mentioned here, but it's one of the key features of modified. I apologize if we didn't text it, but we will add it when we will share the presentation with you. It's the better permeation resistance. So modified PTFE has a better permeation. This, for example, is really useful in seals because you don't want some of the stuff, can be a gas, liquid, that goes through the porosity of PTFE. Porosity is very low, so over years we are talking the permeation of this gas through the bulk. Basically, modified PTFE has a better resistance, permeation resistance. Also in application for in linings, where PTFE is used as a liner inside tanks to protect the metal of the tanks from the nasty chemical inside. Modified PTFE will have a longer life comparing to regular standard virgin PTFE because of its better permeation resistance. How do we trade modified PTFE? It's quite easy. It's a pin. It's a fluted P because we mentioned it. That's PTFE. 1050 and 1550. 1050 is the standard grade. Again, virgin PTFE is P1000. Modified is P1050. So the 50 states the modified resin at the base of the material. That's also for our compounds. We will see. And 1550, it's again 15, it's premium grade, 50 modified PTFE. Oh, this is interesting, guys. So we mentioned modified PTFE as a different change. We add the modificator to the polymer itself, to the homopolymer. Let's see some numbers about this. Basically, we have mentioned in the last webinar that PTFE is as unique manufacturing process because even if it's a thermoplastic material, it cannot be processed by melt techniques like screw extruding or injection molding, but we do have to use our own techniques. Why? Because the viscosity, once you melt the PTFE, the viscosity is so high thanks to the molecular weight, and we can see here the MW states molecular weight is so high that when you get to the fused material, the viscosity, so the tendency to flow of the material is so high that it doesn't flow. When we add the modification, we're talking about the orange column modified PTFE, we add a very small percentage of modifier, less than 1%. This will lead to a lower molecular weight and to a lower melt viscosity. So still modified PTFE is not melt processable, but we are going down. So we are getting more near to the melt processable polymers. Here comes PFA. PFA is, to some extent, almost the same of modified PTFE because it's chain of PTFE. During the polymerization, the modifier will start this ramification to the chain, but we add more modifier and we have a polymer, and you can see it by number, with a lower molecular weight, with the viscosity that is lower, and so this leads the PFA to be a melt processable fluoropolymers. As you can see, just super fast, we will see the numbers. Molecular weight of PTFE is 10 to the 8. When we are talking about PFA, that is the molecular weight. So it's the molecular weight is how long is that chain that we have seen before, the repetition of the entity, C2F4. On PFA, we have 10 to 6, so the molecular weight is reduced by 2 orders of magnitude. The viscosity for PTFE is 10 to the 12, so it's very, very high. It's not viscous, actually. For PFA, we have reduced the viscosity to 10 at the fourth to 10 to the 3. So this leads the PFA to be melt-processable. But we have seen some numbers. Let's see a picture that will explain to you what does it mean in reality. So basically, this is an experiment that was done by Dynon. They had two spheres, one made of PTFE and one made of PFA. They place it in the oven. Once they reach the sintering temperature above 300 degrees, you can see on the left side, the PTFE spheres keeps its shapes. It becomes transparent because it's getting to the melt point, so all the crystalline parts melts and it's a full amorphous material, transparent material. PFA, that was a sphere before reaching temperature, once it melts, it's really melting. So it starts to behaving like a very high viscosity liquid. So the spheres lose its shape and start melting. This is why PFA is a melt-processable polymer, can be extruded by screw extrusion or injection molding. PTFE is not. Oh, the interesting part of the webinar, PTFE compounds. PTFE compounds are really the option where PTFE, because PTFE has some weakness, it's a wonderful polymer, but has some weakness. We mentioned one before, the deformation under load is a weakness point, it's a weak point of PTFE. But what we can do to improve the weakness of PTFE, we can use a PTFE compound. Basically, PTFE has a very high sintering temperature. This is not really helping the selection of the fillers, because the golden rule for PTFE compound is that what we are going to add to our PTFE matrix as a filler has to withstand the sintering temperature of PTFE. Sintering temperature of PTFE is above 350 degrees. This means only few stuff, mainly organic stuff, can withstand the temperature. On inorganic, it's more easily to select the right filler. But just to give you an example, why there is no out there a PTFE plus polyamide plus nylon. Nylon is one of the widest, most used plastic on the world. The answer is simple, because if we are going to add some nylon to the PTFE, once we are getting to the sintering temperature, all the nylon will start burning, degrades. And we don't want a PTFE plus something carbon that has a degradation of nylon or whatever we add. So the golden rule is you can select a filler for PTFE that can withstand this sintering temperature. There are other rules like the granulometry, the shape and everything, but I always like to say this because it's easy to remember also. It's nice. So we do have two big families of fillers and compounds, inorganic fillers and organic filler. Inorganic filler, the most used are glass, carbon, bronze, and also moly, molybdenum disulfide. It's called moly or MO. Okay, who cares? MOS. Also, organic filler can be used. Organic filler, as we mentioned, the range of filler that we can use is smaller because of the sintering temperature of PTFE mainly. So the most used organic filler are PPS, PEEK, the aromatic polyester. You can you know it maybe as ethanol, polyamide, and also a modification of the PPS that is called PPS. There are other polymers, organic fillers that we do use, but these are the most used fillers, organic fillers inside PTFE. But let's talk about inorganic fillers that are really, let's say, 90 or 95% of the market of PTFE compound. Glass fibers. Glass fibers, we can have different form of glass fiber, long fiber, short fibers, also bubbles. The glass is probably together with the carbon, the most used filler for PTFE, but why? Because this is true mainly for all the PTFE compounds, but let's see it one by one. Glass really improves the wear behavior. Another weak point of PTFE is the wear. So if we have a dynamic application using just regular virgin PTFE, it will wear really fast. So when we do have a dynamic application, it's almost anytime better to use a PTFE compound. There are some cases where it can be used also virgin, but 90% of the application, dynamic application, uses PTFE compounds because the filler inside PTFE will improve the wear resistance. So going back to glass, it improves the wear, but it improves also the friction. Improves is maybe the wrong word. The friction will be higher, and it's not always a good thing, but it's not a major difference. It's a bit higher than comparing to the PTFE, virgin PTFE friction. The behavior on compression is really improved comparing to the virgin PTFE, basically because when we applied the formation under load is reduced. So when we apply the load, the fiber will help the PTFE matrix not to slip, and so we will have a better compression resistance. As we mentioned, we can select different kind of glass filler. We can select long or short. That depends on which kind of application we are going to see. If it's a dynamic application, if it's just static, but where we do have to apply the load. This is our know-how, and we are always happy to help you guys to select the right filler for your application. So bear in your mind, we will see also on the next slide. Always, we know, okay, 25% glass fill. It's fine. For 90% of the application out there, just the regular glass fill PTFE is fine. But then if you want to enhance the performance, we do always have the ability, and we are super open to discuss with you guys how we can improve the performance of our seals or our application. And again, contact us and we will be super happy to help you to have a better solution for our customers. But glass has also some weak point. It's an abrasive filler, so glass is really hard, and if we are using, we have mentioned that the wear is improved, so we're using a dynamic application, we will have a counterpart, but if the counterpart is too soft, the counterpart will suffer of wear. So bear in your mind on dynamic application, glass is really suggest because the performance are great, but we always have to think about the counterpart. Better an hard metal when we are making a glass filled PTFE. Also, the chemical resistance is reduced because the glass has not the same chemical resistance of PTFE, so it can be attached by strong alkalis and hydrofluoridic acid. This means that glass PTFE, it's not always the best choice in chemical environment, but only on few applications. Common percentage, we can produce glass PTFE plus glass up to 40% of glass. So we have mentioned that glass is a very good compound, widely used, but has some weak point. When it comes to glass fiber weak points, we will suggest you a carbon fiber additive. Basically, a carbon fiber has almost the same properties of glass fibers, but you can achieve the same performance, the same properties using less filler inside. It's also more expensive, so it's balancing this, but the carbon fiber is not attackable by anything, so the chemical resistance will keep the chemical resistance PTFE, and also is not an abrasive filler. So when you have a dynamic application and the mating surface is soft metal, for example, glass is not suggested, but carbon fiber will be the right choice for you guys. Also, being a carbon, and we will see with the next filler, it has a good thermal conductivity. The percentage of carbon fiber can reach 20% on standard compounds. I am having some problem in uploading my slides, guys. Sorry. Okay, here we are. Carbon. Carbon, as I mentioned at the beginning, is, together with the glass, probably the most used filler inside PTFE, we do have lot of different carbon shape, carbon kind. We do have carbon and carbon co, two big families. Carbon is a lower grade, is a mine product. It's quite cheap, but has a very good performance. It is great for wear application. It's great for flammable environment where it's needed the anti-static properties, because you don't want a spark that can initiate a fire, or it can initiate a spark. Then, so the anti-static properties of carbon, because of its electrical conductivity, is widely used mainly on ATEX environmental. But we were mentioning the difference between carbon, soft carbon. The hard carbon, as I mentioned, is a stiffer material. Soft carbon, that is a more expensive kind of the shape of the carbon itself, will help a lot, mainly on the machining, because it will produce it being kind of softer during the machining. You will wear less the tool. So if we have to produce a very big batch, and the tool wear of the machining can be a problem, because we do have to change the tool, then the setting of the machine is different, then the tool has some cost. Sometimes it's better to use soft carbon, for example. It has some weakness about oxidizing agents, but that's not the main issue. On carbon, the common percentage is 20-25, but we can produce up to 35% of filler. Graphite is a crystalline modification of carbon, is more pure, and the shape is a flat shape. Graphite is widely used for its dry lubricant properties. Basically, graphite will help reducing the friction on dry dynamic application. Because when we do have a sliding application and dynamic application, and we have to have a very good wear, but we do also need some lubricants. So one of the most common can be glass plus graphite, because you will have the improved performance of wear thanks to the glass, but the lubricity, the friction behavior will be great thanks to the graphite. Last but not the least is the bronze filler. Bronze is, I guess, it's probably the best filler for PTFE, but has one problem: the limited chemical resistance. We know that PTFE is widely used thanks to its chemical resistance. So when we add bronze and the chemical resistance is reduced, we cannot use bronze compound everywhere. But the properties are, I would say, the best. We do have the best deformation under load thanks to the bronze filler. The wear behavior is incredible. And this compound can reach up to 60% of filler, mainly in piston seals for pistons, for aerodynamic pistons. Bronze is the to-go material. Of course, we have the problem of the chemical resistance. Okay, we have seen the most common filler inside the PTFE. We also have seen that there are some links between the properties that adding a filler to the PTFE will lead, but we have this table that is showing us what I mean. So we have the different filler on the top and the properties that we have seen that usually are improved by a filler. We can see that almost any filler had a plus on these properties, mainly deformation under load, where the thermal conductivity, the friction that is improved. Remember, it's not always the best thing, hardness, and the dry running behavior. So as you can see, glass is a very good material, but it's not the best, for example, for deformation under load. Deformation under load is really improved by bronze and carbon. So if we do have an application with a very high pressure or a very high load, bronze and carbon will be the to-go materials. The wear, again, it's improved by the hard carbon, the carbon of the mining product we just mentioned before. On the soft carbon, as I mentioned, it reduced the tool because it's softer, but at the same time, if we are using it in dynamic application, it won't have the same performance of an harder and stiffer material like hard carbon plus PTFE or PTFE plus bronze. Thermal conductivity is usually always improved because PTFE is a thermal insulation material. So when we add something that has a better thermal behavior than PTFE, and PTFE is very good insulant. So anything, almost anything that we will add, everything we will add to the PTFE will improve the thermal conductivity. And going back to the dry running behavior, we mentioned two products, the MOS, moly, or the graphite. Those are the to-go filler for dynamic application on a dry environment, so when we don't have lubricants. Out of your knowledge, we are not sharing numbers today with you about the deformation, how much is improved with one or the other compound, how much the wear is improved. We will do it in further webinars. Of course, these are the first webinar, and we want to introduce you guys to our world. And we do have a lot of numbers, we do have a lot of things. So also by your emails or your questions after this webinar, we can set better the next webinar. If you want more number, we can do it, no worries. We just wanted to give you, to introduce you to our amazing world of PTFE and PTFE compounds. Again, briefly, we can see which are on the first row, we can see which is the difference between PTFE and modified PTFE. Mainly, we keep all the properties constant. The deformation under load is reduced. It's a green arrow, so that's a good thing. And when we add the filler, generally speaking, we do improve the deformation under load. We do improve a lot the wear behavior. We do reduce the chemical resistance, and that's not good, or at least it's not always good. Also, the expansion coefficient, and this is a very important thing we didn't mention before. The expansion coefficient is another weak point of PTFE. PTFE, due to thermal changing, temperature changing, moves a lot. So many applications that goes up to very high temperature, then goes down, they don't like to have a seals that moves due to thermal expansion. So adding a filler will reduce the thermal expansion, and that's really good for engineers that have to think about the seals behavior at low but also at high temperature. Thermal conductivity, again, it's a improved features of PTFE plus filler. Thermal conductivity, again, I want to spend very few words with you guys. Thermal conductivity, virgin PTFE is an insulant. A lot of time it's used because of these properties, but many other time, the filler inside of PTFE that will help to have a higher thermal conductivity is the key feature for the application. For example, on engines, car engines, we do have seals on the injector, on the fuel injector. These seals are made usually of carbon or bronze compound, and because they will see a very high temperature, sometimes also 350 degrees. So virgin PTFE, after years and years, will start suffering with the add of a thermal conductive filler. It will help to see the temperature, but also to release this temperature. And this is really important. Mainly, again, what we have done was developing a grade of PTFE with an outstanding thermal conductivity for this application of current injection. And this is, again, to show you that we are always open to try to see if we can improve the performance of our product on the final application. And again, we are super open to receive your question or to receive your project and try to win the project together. Again, I will explain a bit how we do love to work, because we are trying to and we are super happy to share with you our knowledge about PTFE. But of course, there are many people working in fluorseals from very long time and spending all days on studying PTFE compounds, properties, manufacturing process, and everything. So we do have great know-how that we are happy to share it with you. But again, it's a lot of know-how. And what we really want to show you with this slide is that sometimes when it comes an application, for example, a shaft seals on the second row, and we understand that for that application, we need a very good wear-resistant material, low friction torque, so the friction on the first moving static friction has to be low, and the shaft force also low because it's a dynamic application. We do have different material that works, like for example, glass moly, so fluted P7500 ZM is a 20% filled glass plus 5 moly, MOS. This is a great compound. No wonder. It has a very good behavior. It is perfect for shaft seals, but we do have the know-how and we likely to share with you so that we can boost our business together. There are other compounds that performs better. For example, the 7500 GG is made of special fillers that will have an outstanding performance on shaft seals application. And this is one example. Of course, here we are showing you different applications, just as an example with possible material used in that application, actually materials that we always suggest to you guys for those applications. So I thank you guys for attending this webinar. Again, I ask you if you have any question right now. You can just chat me and see if I can help you. But also, if you will have some suggestion or if you want more details on something, do not hesitate to ask us, because we can organize another webinar with more detail, with more number. For example, deformation under load, which is Giovanni, which is the difference in number between virgin PTFE and modified PTFE. No problem. We can share with you. We can organize a webinar. Everything. Let's ask us, and we will do everything to help you. So thank you, everyone. If you have any question, I can answer to you, and you can chat, or we will wait your feedback. Thank you. Thank you a lot. Ma sono rimasti io te. So the first question is why or how or for what reason PTFE is classified as a thermoplastic? Basically, because it is a thermoplastic. It's not well processable. Thermoplastic means that it can melt, so it has some crystalline structure, and once you reach a melting temperature, you will have a melt. The main difference with PTFE is it doesn't flow. There are three big families, and this is another reason why it's classified as thermoplastic: thermoplastic material, thermosetting material, and rubber. Rubber, basically, they are characterized by this, what is called, I don't know in English, it's a disulfide bridge, maybe, that's the exact translation from Italian. And this disulfide bridge allows the very elasticity of the rubber, because the bridge, when you are, for example, trying to elongate a rubber piece, it will come back, and it will come back thanks to this disulfide bridge. Thermosetting material is a material that once it's processed, it will create some irreversible bonding. So if, for example, you have a thermoset material, you heat it up, you process, after that, if you will try to process again, it won't be processable because it will keep its reaction until it degrades. Also, and then we have thermoplastic. Thermoplastic material, generally speaking, they are classified as material that can be reprocessed many times, because once they get fused, if you're going to melt those again, they will melt again. So basically, PTFE is an exception, but you can melt PTFE how many times you want. The point is that it doesn't flow, so it can be reprocessed. It's strange, Marvin, it's a good question, but it's basically because we have this 3D classification of plastics. Next question is, how do you decide the percentage of the filler? Basically, it depends. So we do have standard products that are widely known from the market, widely used for several applications, and we know all the industry know that that percentage of material is the to-go material. But the main reason of the percentage of the filler is the trade-off of the properties. So once we have all the information of the application, which are the goal from our customer, we can set the trade-off between filler and percentage, because we have different filler that we know that affects several properties in certain ways. But when we're going up, maybe we start having lower lower wear resistance or lower deformation under load. It depends mainly from the application data, so we know which we know. We can share it and there's no problem, but the thing is, we do have to understand which is the application requirement, and so we can set the right percentage to get the best performance out of the application. Okay, guys, I don't see any other question. Again, we are super open to receive any comments to improve our work. We are at the beginning of this path together with you. I thank you everyone to participate to this webinar. And again, if you have any suggestion or if you want more details about today's webinar, we are open to send you everything, or maybe organize a new webinar on that specific topic. Thank you, everyone, and see you next time. Ciao, ciao.